All right, let's talk about how we deal with tensions. Okay, so tension. What's going on here? Something weird. That's ugly. There we go. Tension. Okay, we got her now. We got her now, Robbie. Okay, tension is a pulling force in a rope or cable. Something weird's happening. What is going on right now? Auto color changing. I don't know what's happening. It's not cool. I'm not happy with that. Tension, pulling force in a rope or cable. So let's do just a couple of examples. Let's imagine that you have a block of some sort, a mass, and you hang the mass. Okay, so there it is, large, heavy mass. Okay, and then you take a rope. And so if we take a cable and we were to add it in here like this, okay, we imagine that this is like tied to the ceiling. We can actually calculate what the tension in this rope must be. So we'll quickly do that, and then we'll move on to what would happen if that were at an angle. Okay, so if we do a free body diagram, we're going to find that you have weight here, and weight is equal to mg. In this case, 10 kgs times the acceleration due to gravity, and you get 98 newtons, roughly. Okay, so if that's the downward force of weight, then we must also realize that there is an upward force of tension that is equal and opposite to that. We know that that force is equal. We know that Ft is equal and opposite to weight because this is not accelerating, right? It's statically positioned there, just hanging from, a beam on the ceiling or whatever. And there's your free body diagram. So we can then say, if we were to measure this tension directly, that it would also equal 98 newtons in the upward direction. Can you think of a way that we could actually get in there and measure the tension on this object? What's something we could do in order to measure the tension in this rope? How could we do it? Why not take like a spring scale and cut this rope, right? And hook the bottom of the rope on there and the top of the rope on there, and then our spring scale would read 98 newtons. Okay, so that's a way to directly measure the tension in this rope. And something interesting is that regardless of which way we flip the spring scale, upward or downward, it would still read 98 newtons. In other words, this tension force is not really directional. It's always just a stressed or pulling force. Okay, tension cannot ever push. Okay, so that's tension 101. Now let's get into something more interesting. What happens if instead of being suspended by a single rope, okay, what if we suspend it by first two vertical ropes? So, got that and that. So now it's a sign or something hanging from two ropes directly down. And it's 10 kilos here. And let's just assume that these are equally spaced and they are exactly both perpendicular to the surface. Okay? What do you suspect is going to happen here? Yes. Precisely. Okay? So each rope now has half of the force to provide. So 49 newtons, 49 newtons, and 49 newtons. So hopefully that makes logical sense that these ropes would share the load evenly. So, something to note here, right? We're about to do something super fun, but to notice here, what's important is if we look at this in terms of Cartesian directions, we would call the up and down the y and the left and right the x. Okay. Notice that all the forces in this case are only in the y direction. Okay, we have a downward y and an upward y, and the total of the upward y has to be exactly equal to the total of the downward y. in a case like this, okay? So the next question is, well, what happens if instead of just hanging this vertically from two ropes, we now connect them at some point on here and we hang them at an angle? So let's draw that out and see if we can figure that concept out. All right, let's add in some angled suspensions here. So this represents something hanging from like a rope from the ceiling or something like that. And we'll do that. And let's write in some information here. So we're gonna have some angles on this guy. So we'll just say these are the angles we're dealing with. And we'll make them both the same for now. Eventually we'll make them unequal, but for now they're equal angles. And let's say they are theta equals 30 degrees. Okay, and you might get a question like this. It might say, find Ft and Ft prime. Okay, so that is the tension in these angled ropes. So where are we going to start with something like this? Well, I think the best thing to do is write down what we know. So we know this. We still know that the weight here is going to be 98 newtons, just like it was before, right? Still know that. And therefore, what we also know is that the total, we go back to this kind of Cartesian plane idea. This is the y plane, this is the x. We know that the total in the y plane has to equal 0. However, we now have some pull in the x-plane, okay? This comes down to this concept of vector components. If I apply a force in this direction, okay, well, some of that force will be broken up into a component here, aiming upward, right? And a component here, aiming rightward. So Ft prime y and Ft prime x. So now we're going to have some pull to the right. And since this is not accelerating, we said it was a hanging stationary sign, we also realize that there's got to be an equal and opposite pull to the other side over here. So that's just Ft x. And this will also be doing some lifting. Call that Fty. Now, if this is a completely stationary system, then we could say this. We could say that Ft of x, that's this off to the left, must be exactly equal to Ft prime x. The rightward and leftward pull have to be equal. There is no acceleration in this plane. And the other thing we know is that these y components, well, they're doing the lifting. So the x components are working against each other. Y components are working against the weight, okay? So the other thing we could say about this scenario, and I'll just write it down over here because this is a really important part, is that Fty plus Ft prime y, so this and this together team up to counteract the weight. So equal and opposite in direction. So the question is, does Fty equal Fty prime? And the answer is yes, and here's how you have to think about that and why that makes sense. We said over here Ftx and Ft prime x were exactly equal. And if you know trigonometry, if one side is equal and the angles are equal, everything else about those triangles has to also be equal. Correct? So in other words, Fty prime has to be exactly equal to Fty, just by your rules of trigonometry. Okay? And hopefully by rules of logic as well. These are essentially identical scenarios, right? Due to the fact that we have the same angle here. And, you end up with understanding that these two tensions have to end up being equal as well. So yeah, everything is equal. And now from before, okay, we said that if there was two upward ropes lifting this thing, they would share the load equally. So that same concept applies here. Each of these FTYs shares exactly half of the value. So this is actually quite a straightforward problem. What we can do with it is we can just look at one side. And we could say, okay, the y component of Ft, okay, the y component of Ft, So that's that. Okay, and we said this was 30 degrees. Sorry, I didn't draw that in a very good spot. Here, FTY has to be equal to half the weight. So it must be equal to 49 newtons. Does that make sense? And if we want to solve for FT, well, it's just a matter of choosing correctly what trig function to use, right? So what we could say then is we could say that the sine of 30 degrees, that's the opposite over the adjacent. So the sine of 30 degrees, so that's opposite over adjacent. And in this case, opposite is 49 newtons over adjacent. Or we could say that the adjacent angle, no, did I do that right? Yeah, I did. Whoops. Sorry, let's use the right terminology here. Opposite over hypotenuse. That makes more sense. Let's just fix that. Trig. It's so hard. Okay, there we go. So what we get then is the hypotenuse, or in this case, since hypotenuse is FT, FT has to be equal to 49 newtons divided by the sine of 30 degrees. And that will equal 98 newtons. Okay? And since we figured out that FT and FTY have to be equal, or sorry, FT and FT prime have to be equal, then we can deduce that both of these are now 98 newtons. Okay. The only reason that these guys work out to be 98 is because these are 30-degree angles, right? And the sine of 30 degrees is a half. So if these angles were lower, what would happen to this number? If we drop this down to 20 degrees or 10 degrees, what do you think would happen to the amount of tension? Would it get higher or lower? It would increase, absolutely. And if we increase this angle, okay, these values would drop. In fact, if we go to a 90-degree angle, we've actually dropped them down to 49 newtons at that point, okay? And can we ever increase these to 0? Could you ever imagine a system where you have cables and something hanging on it, and you get an angle, you pull this tight enough, you stretch these out till this equals 0? Could that ever happen? What would that imply if these were 0? What would that imply about the size of the y component if that's 0? 0. That would say the y is 0. Well, if we have a value downward, can we ever have a y equal to 0? No, right? Because if we have a y equal to 0, then we have this thing accelerating towards the ground. So technically, I mean, you can pull this to insanely high tensions. No matter what, it's still got to have a tiny little bit of y value to it, okay? So even something like a big, huge, gigantic, fat cable pulled extremely tight, the second you hang any weight on it, it might be like almost undetectable, but you will instantly have a small angle in it because you have to. You have to have some y component in order to have this thing be lifted. Okay, you can experiment around with changing the angles there, and you can drastically change the forces, or the tensions, I should say, in the cables. And that's kind of our basic, straightforward scenario where both angles are equal. So let's see what happens if we go to the more interesting, even more interesting scenario of, of having unequal angles now. Okay, so here we have a mass. And we'll suspend it. Like so. Okay. Okay. So it's going to be a little more involved to solve this. So we'll still make this 10 kilograms just because it's sort of a nice half-decent number to work with. We're going to call this theta. We're going to call this alpha, just to distinguish between the two. I'm going to go ahead and just sort of cut these into two different tensions, and we're going to call this FT, and let's call it FTA, and we'll call this FT. You might also just see it as like T A T B, depending where you're looking. Okay, so first question, do you feel that these will be equal tensions now? Which one do you think will be a larger tension? Who thinks that FTA will be larger? No one? Who thinks that FTB will be larger? A larger amount of people do. Okay, so we'll just say FTB. It's not a good place to put that. Just keep in your mind what you originally thought, okay? So now let's start thinking about the components here, right? So you got weight, which is down here, and it's 98. We've already got that sort of sorted. We're gonna have, just to make, I'm gonna leave the F's off of here just because it's kind of a pain to write all that stuff. So tension B, this is going to be the X component of tension B. So we'll call this TBX. Okay, so there's TBX. We get TBX by saying we're gonna take TB, and we have the adjacent angle, so it's going to be TB cos alpha. Does that make sense? The X component of TB is found as TB times the cosine of alpha. Make sense? And that's going to be pointing to that direction. Okay? And we're going to say the same thing over here. We're going to say that TA X is equal to TA cos theta. And that is going to point in that direction. Okay. We're also going to say that TBY, yes, tacos theta, nice. Okay, TBY aims up and is equal to TB sine alpha. Okay. And the last one's going to be tough to fit in here, so I'm going to draw a little arrow. Okay, I'm going to say TAY equals TA sine theta. Okay, so we've now assigned everything in here a value. We have assigned everything. It's just a very punny day here. Okay, so we've got a force of tension here, a force of tension here, and we've now mapped out all the components and which way they point. So let's say some truths about all of this. We can say that TAX is equal and opposite to TBX, correct? So what we can do is we can just write down here TA cos theta, right? We said that was TAX. So TA cos theta has to be equal to TBX TB cos alpha. You have to be careful because these angles are different. Don't be tempted to put theta theta. Do that, bad things will happen. Okay? And let's also talk about what's going on in the y-plane. Well, we have a downward force of 98 newtons. So the sum of TBY and TAY has to be equal to 98 newtons. So we can also say that. TAY plus TY has to be equal to the weight. Okay? They are not equal to each other though. Okay? Since we have unequal angles, they are not equally lifting. Okay? The sum of them has to be equal to W, but they are not equally lifting. So we can say T A sine theta plus TB sine alpha has to be equal to 98 newtons. Let's make sure that's right. Yes. All right. So now we have a bit of a problem, right? So we have two unknowns in each of these equations. However, what we're going to be able to do here is do a little rearranging and a little substituting. So what we'll do first here is we'll just say, let's make this equal to TA. Well, TA should be equal to, divide cos theta off, TB cos alpha divided by cos theta. Did we assign values for theta and alpha yet? No, we didn't. So we'll do that later. We'll work out all the mental math part of it first, and then we'll do that later. And now if I look, I see over here we have a TA. However, I now have the ability to put it in terms of TB. Okay? So we're going to do a substitution in here now. Where I see TA over here, I'm going to substitute in my little new equation. So what we get, we sub here into here, is this. TB cosine alpha over cos theta times sine theta plus TB sine alpha equals 98. Is this now solvable if we know theta and alpha? Sure, because the only unknown is TB. Okay? How do you feel is the best way to go about solving this equation? Should we isolate for TB first? How will we do that? How would we isolate for TB here? We distribute it out of this part here? I think we can, right? We could say this. TB like that. Could we not just say that, right? Yeah, what's up? And we're back. We have not assigned values for alpha and theta yet. It's really, honestly, irrelevant what the actual numbers are. What is important is that you understand how we got to this point. If you don't, rewind, go through her again, right? Oftentimes, students have trouble with the trig. They don't understand why this is true. If you don't, drag out SOHCAHTOA and work it out. Draw a triangle. Understand why this is true if you don't understand it, okay? It's vital that you get this. Alrighty. This looks like a big angle. Let's call it 50 degrees. And let's call this, 30 degrees. So we're going to go 50 degrees, and we're going to call this 30 degrees. Okay? So then anywhere we see theta, we're going to replace it with 50 degrees. And everywhere we see alpha, we're going to replace it with 30 degrees. So let's rewrite this. TB, which is what we're trying to solve for, should be equal to cos 50 sine 30. Oh, that's not right. That is not right. Make a mistake like that, and your number will not come out right. Lucky we caught that. Okay? That should be cos alpha. There we go. And that should be over cos 50 degrees. And then we get sine, plus sine 30 degrees equals 98. What did I do wrong? It is sine 50, thank you. Holy smokes. Oh dear. Oh yeah. Holy smoke. Are we good now? There we go. Holy smokes. Yeah. Easy to make a mistake there. Super easy. So 50 and 50, good, and 30. Okay, we're happy now. So now we're just going to do this. You're going to have to use your calculator, and you're going to come up with a value for in here. Okay, so let's just pause and do that. All right, so step one, this side, you should get 1.03. Why am I not being able to write here? 1.03, and this is 0.5. So we should have TB times 1.53 equals 98 newtons. And we do a little division here, and we get TB equals 98 newtons over 1.53, and TB equals, I get 64 newtons. So let's scroll back up and pop that where it belongs. So TB equals 64 newtons. Okay, now we have to find TA. Okay? So TA is actually a little easier to find because you made this before, didn't you? So let's just grab this, bring it down, and use it over here. So you know this is true, right? So we can just solve for TA by plugging in our values for TB and our angles from over here. So you don't have to go through the whole rigmarole again. So we've got 64 newtons. We said alpha was 30 degrees. And we said theta was 50 degrees. And I get 86 newtons for that. Okay, how would we go about checking if we were correct? What's one way we could do it? We could see if these two work out to be equal, couldn't we? Does 86 cos 50 equal 86 cos 30? Try it out and see. Does 86 times the cosine of 50, right, that's this, equal 64 times the cosine of 30? If they work out to be the same, we should be good. Or very, very close to the same. There's some rounding here, right? So if you do a problem like this, that's a very quick check. The other thing I guess you could do is 64 sine alpha plus 86 sine theta. Does the sum of that equal 98? And if it does, you're good to go. Okay? So there's a bit of a tricky problem. Sorry for the slight confusion with these values. Hopefully the process is what you got out of here, and that's the main thing. If you got one of these things, could you reason your way through a solution to it? Okay? And that's what we need.